Alrighty, let's do this. So new streak. The last hard problem, I have some ideas for it, but I obviously didn't spend enough effort into it. So new streak. Anyways, count the number of complete components previously solved, I guess. Medium. You're given an integer n. There is an undirected graph with n vertices numbered from 0 to n minus 1. You're given a 2D integer array, edges a, b, denotes that there is this undirected edge connecting vertices at A and B. Return the number of complete components of the graph. Complete connected component. Connect component is a subgraph of the graph in which there exists a path between any two vertices, and no vertex on the subgraph shares a vertex with outside. Yeah, okay. A complete component is said to be a connected component is said to be complete if there is this an edge between every pair of vertices. Oh, between every pair of vertices. So if there was like nothing between the 0, 2 here, it's like 0, 1, 0 to 1, 1 to 2. That's not complete. Okay. So technically this is complete, this is not complete, so there's only one. And if it's by itself, or if it's, if it's by itself, it's considered complete. And it's 50. Okay. So generally when you do these, you do some sort of stack that processes nodes and neighbors onto the stack. Let me think. So is it the case? Is it the case that, let me think about this. I think in order for something to be complete, so if it's like 0, 1, 2, 3, I think it has to be something where each node, if I were to form like all the nodes that are connected within some component, so like 0 connects to 1, 1 connects to 2, 2 connects to 3, and everything in between them, that the number of nodes has to be, if the number of nodes in that thing is n, every node within it has to have n minus 1 neighbors. I think that's true. Every node inside it has to have n minus 1 neighbors. Okay, so let's go ahead and start with graph. I guess this is a 2D array. Normally I can do a default dictionary of lists, but it's going to be, graph is going to be 2D array where the index equals the node, and the value at the index is the neighbors, the list of neighbor nodes. So I guess it should be like an empty list for every k in range n, where n is the number of nodes. Yes, this is 0 indexed. It is 0 indexed. There's node 0, there's not node n. Okay, so for every edge a, b, so for each a, b edge in edges, graph at a, append, maybe this should be a set actually. Maybe I should have a set. So I don't really care about the order. Add b, graph b, add a. Oh. And then maybe I'm just doing counts. So So I think I have a scene, which is going to be false times n. And then I have a process stack. So while process node is process.pop, I think if like when should I do scene if the node is true? I probably should do scene if node is true at the very end. If this node has been seen, then skip processing this node. I think I need to have some sort of current connected components. Current connected components. I also think I probably need to have a for loop actually. For every starting node. Maybe I'll call this root node. In range n, the process stack starts with this node. And then, yeah, I think it should be something like, there should be a current set node process. Actually, this should include the root node actually. So keeping track, so 0 is part of the initial component. And then process node 0. If I already processed this, skip it. And then I would do something like for every neighbor in the graph of this node, current.append the neighbor. I think maybe this should be something like, I think I need to verify that everything has the same branching factor. Branching is going to be -1. I guess, I know, branching should be the number of the length of the number of neighbors for this node actually. Length of the graph of the root. Yeah. So for instance, this 0 is my starting node, and 0 has 2 neighbors. Every subsequent neighbor of 0 needs to also have 2 neighbors. And then I also need to verify that at some point at the very end, the number of nodes in this thing is 3, is 1 more than the branching. Otherwise, it could be, in theory, if every node in this thing has 2, but there was like actually, you can build something that's like size 4. There's 4 nodes, and everything has 2 neighbors. That's still not obvious. That's obviously not complete. So yeah, I guess maybe I don't need to know the actual nodes themselves. I just need to know the count, the number of times I've processed. So maybe I start with count 1. And I do something like count plus equals 1. Okay, so the node there, if I've already seen it, then skip it. for every neighbor in the graph of the node current. Should I increment the count here? I think I actually should say process appends this node. No, process append this neighbor. Whoops, that was going to be pretty bad. I think that might be it. Oh, I complete is initially assumed to be true. And then every time I process a node, then I need to check that the branching factor for the node is correct for every neighbor in the graph of node. If C node is true, I think I do it right here. If the length of the graph of this node doesn't equal the branching factor, then complete is false and break. Okay. And then otherwise, so I go process 0 has branching factor of 2. Process 1 has a branching factor of 2. Process 1. I mean, I probably should do an if statement here. Like if scene of this node is true, then continue. Okay, so maybe I don't do this one right here. And I just say C node root is true. Actually, I should also do it right here, right? If scene for this root, can continue. Process the root, process starting with the root. Count is 1, branching factor is the number of neighbors for this root node. I assume that this is going to be complete component. And I also set the scene of this root. I generally like to put this immediately after the if statement that it checks against. I'll process, node of process, pop, break there. Every neighbor, if it's not already seen, then if it's already seen, skip, process. I need to do another one here. Oh my God, I'm so stupid. I need to. If for every neighbor in the graph of the node, if I've already seen the neighbor, continue. Now I say scene of the neighbor is true. Process appends the neighbor. Oh, plus equals 1. Scene of the node equals. I don't think I need this anymore. And then I say if complete and the count is equal to branching factor plus 1, then the answer increments by 1. The answer is initially 0. That hopefully is correct. Oh my God. Hope denied. All right, go ahead and just verify that my graph is correct. Okay, 0 connects to 1 and 2. 1 connects to 0, 2. 2 connects to 0, 1. 4 connects. 3 connects to 4. 4 connects to 3. Last one is empty. Okay. I think I might have it the reverse. Whoops. I think I might have it reverse. If the count is equal to the branching factor is 2, 3 elements. Should be right. So process 0, length of this thing should be 2, which is the same. So if the length isn't the same, okay, that should be fine for every neighbor in the graph for this. If I've already seen this neighbor, skip, seeing if this neighbor is true, process append the neighbor. Oh, I actually don't know why this doesn't work. So it goes 0, 2, 1. Mm-hmm. Okay, so started with root 0, process 2 and 1, which were neighbors to it. After it, the root is 0, the count is 4. Incremented too many times. Yeah. Because root is actually processed, it should be 1 after that. So, okay, hopefully that was the issue. I don't know if this is really that fast, but it's reasonable, I think. Okay, unreasonable answer. 1, 0, interesting. Somehow I got 1, even though there was 0. Somehow I got 1, even though there was 0. Node 0 connects with node 1. I probably should draw this out. So 0 connects with 1. 1 connects with 2. 1 connects with 3. 2 connects with 4. 4 connects with 3. Wow, that really should be false. That really should be false. 0 connects with 1. Odd. Because 0 connects with 1. 1 connects with 2. It shouldn't really hit this post condition until it processes all the connections of 0, which should be 1, 2, 3, 4, really. So I'm not sure why this is hitting so early. Oh, I see. even though I break early because I detect that this component is never going to end up being complete, I end up not actually processing all the nodes. I see. So I shouldn't break here, is the conclusion. I have to process everything within some component. All right, I think that probably should be the last mistake. Okay. All right. I mean, not incredible, but not bad. Very obvious things I should be doing here. Graph of the neighbors, set of A, B, B, A. Create the graph, 2D array, scene for every starting root. If I've already seen this root, then skip, set it to true, create a process stack, the root, count the number of elements within this component, initially 0, get the branching factor for everything inside this component, assuming it's complete, and have a complete equals true. Process the top of the node or process the node. If not correct branching factors, this is going to be false. And then figure out the rest of the components. Process appends the neighbor. Count plus equals 1 if it's complete, and count. Okay, yeah. So this is, that's a wrap. So summary, this is fairly kind of straightforward. Was this a breadth first search? Breadth first search of nodes. Nodes connected to starting node in a graph. Use the for loop, or first create a data structure to easily access the neighboring nodes from any starting node. I use the 2D array called graph, which is this thing right there, by processing the edges array, and then use a nested for loop where outer loop iterates over each kind of starting root node. Have some tracking for which nodes have been processed or seen. So technically that's this array, or this array of booleans, false, times n for the number of nodes, answers the count of complete connected components. Obviously, when you do the scene, you probably want to skip the nodes that you've already seen as a starting point for processing any given root. And then for each starting or for each kind of root node, to kind of determine if that node is a part of a complete connected component. Use a back with that initial node. Process its neighbors using breadth for search. So when you do that, you have while process, and then basically pop the current node from the back of the list, and then like for every neighbor, add that neighbor to the process in a very general sense. And then there's some checks for whether or not any given neighbor is already processed. Yeah. And then also track the kind of branching factor. So every node in a complete connected component must have the same number of neighbors, right? If every node connects to every other node, then they all have to have the same amount of neighbors. Yep. Same number of neighbors. And that's one condition. And then the other condition is that the total number of nodes in a component is one more than the branching factor, than that branching factor. So if every node has two neighbors, then there technically should only be three nodes that has that. Otherwise you're dealing with a not complete component. So that was using count, and each time I process, I increment the count, and afterwards it has to be complete, which is the flag for that being false is turned on inside the process, and also the count has to be one more than the branching factor. And then increment the answer count for the number of complete connected components if both conditions are true after processing. All right, time complexity is going to be O of n plus e, I guess, where n is the number of nodes and e is the number of edges, right? When you do the process, you only process each node once. Yeah. As protected by the scene array / usage protects against the repeated processing of a node. Space complexity can be O of n, since we use a tracking for scene and also the process stack can technically hold up to n nodes in that. So, all right, cool beans.